Okay, so last time we talked about the monomial symmetric functions, and recall quickly, let's just order them by degree here. So let's just for the moment not worry about the number of variables. So n, remember, is a number of variables, so I'm just going to assume n is some large number, okay, maybe 100 or more, so that I don't have to worry about it too much. Now let me look at the various monomial symmetric functions. So let's arrange them by degree first. So what are the monomial symmetric functions of degree 1? So I'm going to try and list a few monomial symmetric functions, symmetric polynomials. Okay, so this is now going to be the monomial symmetric polynomial m indexed by lambda. And what should lambda be? Lambda should be, well, it's a weakly decreasing n tuple. Okay, n is some large number, I don't care. But the key point is the degree is 1. So this should be something whose, the sum of the lambda i's has to be 1. Okay, which means there's really only one choice, which is 1 itself. I mean 1 in the first component. And since I've assumed that the number of variables is 100, the remaining 99 entries are zeros. Okay, so this is the monomial symmetric function m sub lambda. Okay, and I'm not writing the variables x1, x2 till xn. So this is the degree 1 guy. Now what does the degree 2 guy look like? Well, the monomial symmetric function should be again weakly decreasing sequence lambda such that the sum of the entries is 2. Okay, so that's 2 0 0 0. Or there's another possibility. I can have 1 1 and all the others are zeros. Okay, so there are two of them in degree 2. Now let's go on, look at degree 3. I have m 3 and all zeros, or m 2 1 and all zeros, or m 1 1 1 and all zeros. Okay, and you can already sort of see where this is going. So this is when I look at a general number, or maybe I'll just say I take 4. I have to look at all partitions of 4, all ways of writing 4 as a sum of 2 2 and all zeros, 2 1 1 and all zeros. Finally, all zeros. So there are 5 of them here. Okay, now more generally, if I look at keep going like this, and if I pick some d, then I'm going to run over all m lambdas, where what is lambda? Lambda is going to run over all partitions of D, but of course, I can only allow lambda to have at most n non-zero parts. Okay, and I'm supposed to append it with 0 for the rest. Okay, so of course this is not going to be a constraint if n is very large compared to D, but in general D may be very large too. Okay, if D is bigger than n, then of course you won't get all partitions of D, but only those partitions of D with at most n parts. Okay, so this is the general picture here. But now what I want to do today is to talk about two other classes of symmetric polynomials other than the monomial ones, and these are called the elementary and the complete symmetric polynomials. Okay, so let's define these new classes. So let's fix n. Okay, and I'll fix variables x1, x2, xn as before. Okay, definition: the elementary symmetric polynomials polynomial e sub d, let's say, is defined as follows. Let's go in order maybe. What is e sub 1? polynomials. E sub 1 is defined as follows. It's just a sum of all the x's, x1 plus x2 plus xn. So this is the first guy, E1. How is E2 defined? Well, E2 has, so this fellow has degree 1. How is E2 defined? It has degree 2, and I do the following. I take all products of variables, okay, xi, xj. Now I should sum, for it to become symmetric, I should sum over all possible pairs ij, and I don't want to repeat it, meaning I don't want to think of x1, x2 and also take x2, x1. Okay, so in order to ensure I only get one of those possibilities, I will just put I less than j. So what sorts of terms will this have? x1, x2 plus x1, x3 plus x2, x3 and so on. Okay, all possible sums xi, xj. So this fellow has degree 2. Okay, now let's look at the next guy, degree 3. That's E3. How is E3 defined? Well, products of variables 3 at a time. xi, xj, xk. Now it sort of gets cumbersome to do this in general, so I'll call the variables I1, I2, I3, and again to avoid repetition I'll just say let me only take I1 less than I2 less than I3. Okay, and more generally the degree D elementary symmetric polynomial is defined as xi1, xi2, xid, ranging over all possible numbers I1, I2, ID inside the set 1, 2, 3 till n. Okay, and observe this of course only makes sense, or you can only define this provided d is smaller than n. Okay, so this is provided d is n or less. Okay, and observe what is En, the very last guy. En is just going to be a single term, x1, x2, xn. That's the only thing you can get for En. Okay, and if it's bigger, then you just define it to be 0. Ed is 0 if d is bigger than, okay, because you can't really take products of variables more than n variables there. Okay, so this is the definition of the elementary symmetric polynomials. Now of course they all have, so observe what we have done so far is only produced one in each degree. Okay, so that's slightly different from what we did in the what we saw for the monomial symmetric polynomials so far, because in degree 1 there is 1, in degree 2 there were 2 of them, degree 3, 3, 5 and so on. In general degree D you have p, d, n number of them, right, as many as there are partitions of D with at most n parts. Here I produced only one in each degree, that too only in degrees 1, 2, 3 till n, that's all. Okay, good, but we'll come back to this point. Now here's a lemma which says where these come up. In fact, they come up in, for example, the theory of equations, when you try and find roots of a polynomial and so on. When you have a polynomial and you know its roots, then you know how to factor the polynomial into the product of the roots. So the roots are alpha 1, alpha 2, alpha n. Then the original polynomial is just x minus alpha 1 into x minus alpha 2 and so on. This is more or less the same statement, just phrased a little differently. So here's the lemma. Compact way of getting all the elementary polynomials in one stroke. It says consider the following product: 1 plus tx1, 1 plus tx2 till 1 plus txn. Okay, there's one term for each variable, and ask yourself what will you get if you expand this product out. Okay, and I want to expand it out. So t, what I've done, I've introduced a t here that should be thought of as a new variable, okay, some formal variable t. And what we're going to do is to try and expand this out in powers of t. Okay, so what's the smallest power of t you can get? Well, I can get t power 0, that's the constant 1 here. And what's the largest power of t I can get? Well, I can get n, right? Okay, now let's see if d is some number between 0 and n, what is the coefficient of t power d here? Well, the answer is, how do I get a t power d term in this product? I get it by looking at, so if how will I get a t square term, for example? I will get it by picking t from one of the brackets and t from one of the other brackets. Okay, when I do that, the coefficient that I will get, so I pick t from this bracket and the t from the other bracket, the coefficient that will get will just be x1, x2, right, the things that are in front of the t. Similarly, if I pick t from the first bracket and the t from the last bracket, then the coefficient I'm going to get is just going to be x1, xn, and so on. Okay, so in general, what I'm doing here is, to get a particular power of t, if I want t power d, I have to pick out t from d of these n brackets, and doing so will give me the corresponding product of the xi's. Okay, so you should convince yourselves that the coefficient of t power d is exactly what we have called ed. So this is exactly the elementary symmetric polynomial ed in these n variables. Okay, so that's the expression here. Okay, and proof is more or less obvious, just what I gave you right now. Okay, so this is just a compact way of packaging all these elementary symmetric polynomials together in one stroke. Now let's move on to the complete symmetric polynomials. So that's another class, that's the next class of polynomials, so sometimes called the complete homogeneous symmetric polynomials. So let me just call it the complete symmetric polynomials of degree d. Again, let's just list them degree by degree. So these are just like the e's, the notation here is h, so we call them h1, h2, h3, and so on. Now how is h1 defined? Well, h1 of x is, well, it's actually the same as e1. I just take x1, x2, xn, all of them, degree is 1. h2 of x, so x, recall as before, is just shorthand for the variables x1, x2, xn. So how is h2 of x defined? Well, here's the definition. I take all possible monomials x to the alpha whose degree is 2, okay, such that summation alpha I is 2. Okay, what does that mean? How can I get total degree 2? Well, I can look at, for example, x1 square or x2 square and so on. Right? I can square a given term, or I can take two different xi's and multiply them together. So plus I can take all possible xi, xj, like before, I less than j. Okay, so here I have one additional term in comparison to the elementary symmetric polynomial, which is the square terms. Okay, now more generally, how does one define hd of x? Well, the same definition. I want to take all possible monomials x alpha, alpha ranging over monomials such that the degree of that monomial is d. Okay, observe, here's another simple way of stating the same thing. If I fix hd of x is actually nothing but the sum of all the monomial symmetric functions m lambda of x, where what is lambda now? Well, lambda is a decreasing sequence, a weakly decreasing sequence whose sum is d. Okay, in other words, I should just say it is the sum of all the lambdas which are in PDN. Okay, this is just by definition, more or less. Okay, so that's my hd of x. Okay, now let's again see what this will mean in terms of a more compact expression. Before that, note the following fact: unlike the elementary symmetric polynomial, hd of x is defined for all d greater than or equal to 1. Okay, unlike the earlier one, which was only defined for, ed only made sense for d at most n. Now this is defined for all d. Okay, now let's try and write out the analog of our lemma here. Okay, how do we package all the h's together? Well, the statement now is the following: I take product I going from 1 to n, still the same sort of product, one term for each variable, but now the variables or the terms that I need to take are as follows. I look at 1 over 1 minus txi. Okay, and this is now to be thought of as a formal power series. So you've seen formal power series before in the course. So I'll come back to it when I expand this out. My claim is that when I take this product 1 over 1 minus txi, then what it gives me exactly is the following: d greater than or equal to 0, t power d, hd of x. Okay, and in fact I can, to make this more precise, I should say, oh, it's actually also defined for d equal to 0. I just say, okay, how do I define h0? I define it to be 1. I just extend my definition here. Okay, so let's prove this lemma in this case. Now, proof. So what's the formal power series here when I have 1 over 1 minus txi? What do I mean by this? This is just the infinite power series t cubed xi cubed and so on. Okay, so this is just the formal power series expansion of 1 over 1 minus txi. Now what I'm supposed to do is to take products of all such guys, right? So let's do that as well. So consider the product I equals 1 to n of these terms. Now we ask the same question. If I want to expand this out, now this is going to be a power series in T, not a polynomial anymore. And now the question is, what's the coefficient of T power D? Okay, earlier it was sort of very obvious that it was ED, but in this case, let's think a little bit more. How does one obtain the coefficient of T power D? Okay, again the same thing. So from the very first term, here's what I should do, right? I should take, let's say, so imagine I had the first term 1 plus tx1 t square x1 square and so on. From this term, I should pull out some contribution. Let's say I take the term t power alpha 1 x1 power alpha 1 from the first term. Okay, so let's select that. So I have chosen, oops, can't see. So let's say I chose this term from the first bracket. Okay, now what term will I choose from the second bracket? Some such term, similarly tx2 blah blah blah, t to the alpha 2 and so on, from which I choose, let's say, this one and so on. Okay, so I keep going like this until from the last term I choose some txn. Let's say I choose t alpha n, xn power alpha n and so on. Just this. Okay, good. So now from all of these brackets I've chosen one term each, and since I'm finally interested in the coefficient of t power d, I should ensure that the t power alpha 1 plus alpha 2 plus alpha n, they add up to d. Okay, so therefore, thinking for a moment, you realize the following: the coefficient of t power d in the sum is nothing but the sum of the sum now ranges over all possible alphas. So I can take any alpha 1, any alpha 2, alpha n. They're all, of course, non-negative integers in this case. And what do we get? x1 power alpha 1, x2 power alpha 2, etc. xn power alpha n. And since the total power was d, I conclude that I'm not taking a sum over all alphas such that summation alpha I is d. Okay, I'm only summing over those alphas whose sum is d. In other words, what am I doing? I'm saying that this is just the monomial x power alpha, where alpha ranges over all multi-indices whose sum is d, or all monomials of degree d, and that was exactly my definition of hd of x. Okay, So this proves the lemma in this case, that here's a compact expression for HD. Okay, now let's return to this statement I made right at the beginning, that unlike the case of the monomial symmetric functions, the elementary and the complete symmetric polynomials, I have only defined for you one in each degree. Okay, so degree 1, there's only H1, there's only E1, right? Degree 2, similarly, I only have E2, then E3 and so on. Okay, now let's remedy this a little bit as follows. So we have degree, so let me look at the elementary guys. So let's talk about the elementary ones first. So degree 1, I had E1. Okay, in degree 2, I had only E2, degree 3, E3 and so on. Okay, but let's also define one more element now. So let me define for you an additional element in degree 2. Okay, and this fellow is not going to be a single elementary polynomial, but rather a product of elementary polynomials. Okay, so what should I get? What should I do in order to get you something of degree 2? Well, if I take E1 into E1, the product of E1 with itself, then that's going to be of degree 2, because of course E1 is of degree 1, so E1 square is of degree 2. Okay, similarly, let's see, how do we get an elementary polynomial or a product of elementary polynomials whose degree is 3? Well, we can take E2 into E1 and we can take E1 into E1 into E1. Okay, now both these additional guys both have degree 3. Okay, now let's do the same thing in general. So here's a general definition. Okay, there's ED, of course, that's the original guy, but I can define these analogs, which are as follows. So I will define it for you like this. So let me define something called E sub lambda. Okay, what is E sub lambda? By definition, it's a product of the elementary symmetric polynomials E lambda 1, E lambda 2, E lambda k. Okay, so I am suppressing the variable x in all these definitions. So these are going to be the new guys I'm going to look at. And what should I allow lambda to vary over? It's enough to look at decreasing sequences, lambda 1 bigger than or equal to lambda 2 bigger than or equal to lambda 3 and so on, because I don't want repetitions again. E2 E1 is the same as the product E1 into E2, right? So when I'm going to try and manufacture new polynomials like this, it's enough if I restrict my attention to those lambdas which are in decreasing order. So let's make the formal definition. Given a partition lambda mean PD, so remember, partition of course means lambda 1 greater than or equal to lambda 2. Okay, it has some k non-zero parts. Define the elementary symmetric polynomial E lambda, okay, of x to be okay, and likewise we define H lambda, the complete symmetric polynomial, by the same idea. It's just H lambda 1, H lambda 2, H lambda k. Now these guys, both of these are homogeneous symmetric polynomials of degree t. Okay, so observe, note, degree of E lambda is the same as the degree of H lambda equals D. So of course there are sort of some slight subtleties here which we will come back to later on, which is that say I'm sort of assuming that my number of variables is large. Okay, otherwise, for example, E lambda would not make sense, right? See, suppose I only had few variables, say n equals 3, and if lambda is 7, okay, then E7 doesn't make sense if I only have 3 variables, right? So remember, ED only makes sense if D is less than or equal to n. Okay, so it's sort of modulo that that thing. So I should say degree of E lambda is this equals D, provided n is bigger than all of these numbers. Okay, so or maybe the simplest way to say this is to say, let's just assume that the number of variables is very large. Okay, so this only makes sense if lambda I is less than or equal to n. So maybe should I just put that in there? Okay, so assume n is large. Just say it that way for now. Okay, so I'll come back to this. I'm just trying to give you a sense of where these polynomials come in from. Okay.